In this lesson, we're going to do more volumes of rotation, but we're going to have to do it from a slightly different approach because there are going to be times when we're not allowed or not able to solve our equation for y in terms of x or for x in terms of y, and we're forced to go about choosing a different way to do it. So looking first at this example here, we see that we want to rotate the equation x minus 1 squared minus 1 around the line y equals negative 3. Now this is just like we did before, and so our first step is going to be basically redraw our function, reflect it, rotate it around our axis of rotation. So the inside radius, we're going to think about that as the line going from our axis of rotation. In this case that's y equals negative 3, and going up to our lower curve to get the inside radius. So we can write our radius, we want it in terms of y. Notice that we're slicing again along the x-axis here because that's the way that our radii are being stacked there, or our rings are being stacked in that direction. Next we'll look at our outside radius, and this time the outside radius is always going to be 3. And then we could set up our integral just like before. The outside, the longer radius minus the lower one, which will give you the smaller radius, integrate to find the answer. Okay, now let's look at that same function now, but let's rotate it around the line x equals 3. If we're rotating around x equals 3, if we try to find an inside radius, well that's fine, but notice we're going from 3 back to the curve y equals x minus 1 plus 1. If we're taking the outside radius, we're going to the same curve. Well, okay, we've done that before, and what we were able to do is split this up and maybe try to solve this thing for x in terms of y, and maybe try to do it the other way. The problem is we're not going to be able to solve this. If we try to solve the function for y, when we multiply it out, we're going to get x squared and x. And I just can't solve that for x in terms of y. And so I've got a little bit of a problem here. We need another method to do this. Okay, so if we're rotating a region that contains the blue function f of x over the red function g of x, if we're rotating that around the y-axis, we're rotating it this way, notice there's going to be a hollow center. So the shape that might come from looking at shells might look something like this. Notice the bottom function there is matching the lower curve, and the top's just touching in that region between A to B. And notice that this is hollowed out so that the thickness of this is only going from A to B. Now if we take a cross-section of this then, like we take this orange region, it's just looking at when we're at B, when x is equal to B, we get this big ring that's wrapping around it. When we're inside at A, we get this pink region. It's a lot smaller, a lot narrower radius there, the radius going from the x-axis over to A. And so each one of those rings, we move from left to right, we're just taking the rings from A to B. The thickness of these rings then is a change in x. And the radius of those rings is actually our x value. Okay, so our radius of that first ring is A, and the outside ring, the orange one, is B. If I pull one of these rings out, so the reason we call this shells is because they're like a cylinder, they're like little shells, we keep putting them together and they keep growing. But notice if I lay any of these things flat, they become a rectangle where the height of my rectangle corresponds to the height between the functions, and the base of the rectangle corresponds to the radius, well actually the circumference of our shape, and so it's based on the radius. Okay, so we're getting solids that are coming from wrapping rectangular strips around each other. Okay, so these are rectangular strips, they're being wrapped and so each one is getting progressively wider here and so maybe outside of here I have very thin strips that are very, very long, whereas on the inside they might be taller and shorter. Of course, that depends on the function. The key then is that the area of each rectangle is going to be based on a base times height situation, where the height is actually the distance between my functions over here. Okay, there's my distance between my functions. And then the base of these is the circumference of the circle. It's being wrapped around here, but we could think about that as 2 pi r, where the radius is marked on my picture. Okay, so let's work through the basic steps of one of these problems. Now, first we want to sketch a cross-section like before, and to do that we're going to start by drawing the shell heights parallel to the axis of rotation. So if my axis of rotation in this problem, I'm revolving around the x-axis. Now this one's not going to have a hollow center, but the heights are always parallel to that. So I just choose a spot somewhere along there to draw kind of a random height. And then next I'm going to draw a radius from the endpoints to the axis. So if I'm thinking about the radius of this, my radius could be drawn on either side. Notice in this case that is a y value. And then the last part of this is I'm going to draw rings to spin around of here. And so my rings are going to be going from where my function is and down so that it's kind of reflected over there. And I can draw that on both sides. And I can also draw the other side of this. Notice then that my function is going to kind of end up looking reflected like earlier problems. And so I'm going to get a large series of these rings that are stacking up all the way down to the end of this. Okay? But the important thing, if I just draw one general cross-section, I've got my height that's parallel to my axis. And I've got my radius that's drawn perpendicular to that axis. Okay, so now what we're going to look for is a formula for the area. Now this one's actually going to be in terms of y. And the reason this one needs to be in terms of y is because we want to look how the shells are kind of stacking, how they're growing on each other. Each shell is progressively getting wider here. Notice these small changes in the values. The shell thickness is a change in y. And so it's dy that we want, and so everything needs to be in terms of y. Next we want to look at the radius of these. And the radius here, notice, is coming from the axis, again, perpendicular to the axis, out to where our height is drawn, which is h. Notice then that that is simply y in this one. So if our circumference is 2 pi r, then we're looking at 2 pi y. Our height might be a little bit more tricky here because we're starting here at 4 and we're going back to our curve. So what we're looking at then is this part here is x. We're really taking for our height 4 minus x. We need it in terms of y, and so we're going to write that as 4 minus our function. Our function here was 4 minus y squared. And so for our area of this, we would continue by taking our height times our circumference. Our limits of integration then are the y values. So we're looking at the y-axis from 0 to 2, and we could set up our integral to find our values. Okay, real quickly here then, we want to set this up. This is our axis of rotation right here. And so I want to start by drawing a height just anywhere in here, and that should be parallel. So I'm just taking a general height here from top curve to bottom curve. I'll call that h. Next I want to look at my radius, which can really be drawn anywhere in here, but it's from my axis of rotation, perpendicular, and out to my height. And I can draw that both top and bottom. Next I'm going to be rotating this around an axis, so I'm kind of reflecting this thing, and my height's going to reflect to about the same spot, and then I'm going to have some rings going around this. And so if I stretch this thing out, this is going to be really long and skinny, where my height is based on this h over here, which you'll notice that that height is actually a y value. But it's not exactly y. We've got a negative value here, and we're going to be subtracting there. What we want to think about is our top function minus our bottom function. And our top function here is actually the axis y equals 0. So my height here is going to be 0 minus y. If we think about our radius then, the radius is going from our axis of rotation here at 3, and then we're taking away whatever our x value is. So the radius is just 3 minus x. If we want to think about the circumference of this then, which we are going to need, our circumference will be 2 pi times that radius, 3 minus x. Our area then is going to be our circumference times our height. But we need to decide which variable we're using here. Notice that our shells are going to be growing according to the height in this direction, which is a dx value. Right? We're splitting the x-axis there. And so we need everything in terms of x. So my circumference is fine, but my height is going to have to be written by substituting our equation in there. So 0 I'll just leave out and make it negative. Our function was right here, x minus 1 squared, and then minus a negative 1. Our last step then is to plug that into our formula for volume. And when we do that, we consider our limits of integration. Remember again that these were the x values, and if we look how x was growing, we were starting at 0 and going until we get to this value, which is actually the number 2. My mistake. Because we want to stop not where our axis is, we want to stop in the region that we're using. So how do we choose if we should use shells or the other methods that we've already learned, the washers or the discs? Well, to choose, maybe look at your picture and decide if you're using discs or washers. And those are usually the easier ones to use. So using that model, think about, do I need to integrate with respect to dy or dx? And then try to set up the equation. Now sometimes it's not going to be possible to solve it for x or to solve it for y, which will force you to try switching to the shell method. One of these methods is going to work. Usually we use the shell method when we can't use the washer or disc method. This is going to just change your variables so that it makes it easier. If you want to, if you like this method, it's fine to just choose to do the shells first. But again, sometimes it's not going to work, and you'll have to switch back to washers or discs.